Hi everyone and welcome. Today we're going to be introducing the concept of stack and process stack. Now, a stack is a data structure where items are added and then removed in reverse order. Last in, first out. To add an item, you will need to push it. To remove an item, you will need to pop it. Simple enough, right? Now, if your stack was an array, using pseudocode, you would be pushing the first element, and then the second one, and then the third one. Now, remember here, last in, first out. Last in, first out. So if you were to run a pop, you would be getting 30, and then in order 20, and then again, if you were to run pop again, you will be getting 10. And at this stage, your stack will be empty, right? Let's have a look at what happens in memory when you run your program. If you've been watching the previous classes, you know already that the BSS is for data that has not been initialized, the data is for data that has been initialized, and the text is for the body of your program. Now, in iMemory, you find the stack, which always growing downwards, and the heap, which always growing upwards. These two sections are not supposed to collide because if they do, the program will crash. Let's grab more information about stack and heap. The heap is for dynamically allocated data, reference types, objects, JRE classes, and so on. It is not automatically deallocated. The garbage collector runs here to remove objects that lost their references. It grows upwards, it's slow, and it's not thread safe. The stack instead is automatically allocated and deallocated. Primitive types, call frames or function calls, references to heap objects, and so on. It grows downwards, it is fast, and thread safe. And those are the instructions you can use to add or remove elements. Now, this is the pointer at the stack and it grows downwards, which means that every time you are popping elements out of the stack, you're going to increase your pointer by a quad words, which is 8 bytes, so that your pointer is going to be pointing at the next element. And every time you are pushing element into the stack, you're going to decrease the value of your pointer by 8 bytes, a quad words, so that you're always going to be pointing at the next free slot. And that's a very simple example. We're going to have a look at a more complex example in just a second. That's our program. So we have an array with 3 elements, a flag or bookmark if you prefer, and the RCX, which is going to be used by the loop instruction. So we grab the first element out of the array and we push it into the stack. We increase the flag and we loop. So next time we grab the second element out of the array and we push it into the stack again, and so on until RCX becomes 0. And the pop is similar because we pop an element out of the stack and we store it into RAX, and then we copy the RAX value into the array, and then we increase the bookmark again, and so on. Let's analyze this code using the debugger. Okay, we are in, so I guess we can set breakpoint here. We run it. And then, for example, we can try printing what's in the pointer, and it's 1,000, right? So we just grab 1,000 out of the array and we put it into the stack, right? Okay, so we keep on cycling and let's see now, 1001, same thing, right? Keep on cycling again. And now if I do okay, and printing, we have 1002, right? Okay, now the cycle is off. Why? Well, because that's 0, right? This one is now 0. And we go on and we have the pop. If I do and print this one, I'm gonna get 1002, which is correct because 1002 is the last element that we inserted, right? And again, and again. Okay, now let's try printing RBX instead, right? And we use this one. So we print 5 decimal of RBX so that we grab 1002, 1001, and 1000. So I hope you've enjoyed my class. Please like this video if you like it and subscribe it. And thank you very much.